Hi, my name is Trung, and I am here today to present my project for Deep Generative Model class. In my project, I look at how to sample from autoregressive models efficiently without losing the quality. Now, autoregressive models, as we know, are models that specifies the likelihood based on chain rule as a product of conditional probabilities. These conditional probabilities are typically modeled using the same neural network, and then the autoregressive properties are upheld using masking. Um, the class of autoregressive models are known for slow generation because in order to sample, you have to sample one dimension at a time um, before you have a full sample. Recent research suggests that we can do better, and to do that, we look at a class of models called auto-agnostic, autoregressive models. The key idea here is that your model can take a permutations of dimensions and ordering as input, and then you're able to train the model to learn from a space of all the orderings that you care about. In this case, we sample the ordering uniformly in across the space of all permutations, and then you trained or sample an autoregressive models as normal. So why do we care about autoagnostic autoregressive models? The reason is because of a technique called parallelized sampling. Um, the key idea here is that let's say you have an autoagnostic model and the data dimension is 6, and you have sampled 1, 2, and 3. You can either sample 4, then 5 given 1 through 4, then 6 given 1 through 5, or you can sample 4, 5, and 6 at the same time given 1, 2, 3. Now, obviously, that is going to incur a cost in terms of the likelihood of your sample. But the nice thing about autoagnostic models is that you can compute this loss explicitly, how much likelihood you're losing. And therefore, what you could do is, given a fixed number of steps that you're allowed to sample, you can actually optimize for the most optimal path to sampled in order to incur the least likelihood lost. In the original paper that published this technique, which was from Google 2 months ago, they used the diffusion model as their autoregressive model, and I am interested in looking at convolutional neural networks and whether we can apply the same techniques and get good samples out of it. Because images are known to be has a lot of regions with the same color, and convolutional neural networks can learn about local features very well. So for my model, it has 6 blocks of convolutional layers. The layer inputs are masked to hold the autoregressive properties. The masks are concatenated with the input for the model to learn about the mask, and each blocks are connected with each other via dilated convolutions as well as residual connections. And the reason for dilated convolutions is to keep the spatial dimension of the features the same at 28 by 28 in 4 minutes, because that will let us implement the convolutional layers more easily. So the data set is the grayscale minis, and here are the results. The top left picture is from the training data, so this is just the data set. The top right is from my model trained on a single fixed ordering and sample on a single fixed ordering. It has pretty good quality, and this is expected because we've known that these models can do this for a while. The bottom left picture are samples from my model trained on random permutations and sampled on random permutation. And as you can see, the quality is very low. You can make out a few digits here and there, like an 8 here or a 9 there. But in general, it's pretty bad. And I'll explain why in a bit. Um, the problem with this is that the parallel line sampling technique, this observation here, depends on the fact that the model is high quality, it's well calibrated, and it's learned the data distribution given any ordering. And that's why what you see here on the bottom right are samples from my model trained on random permutations and sampled in parallel, restricting the number of steps from sequentially 700 steps to just 20 steps. And the quality is very low because the model is not well calibrated, and the optimal step end up being taking a bunch of small steps and a huge steps that give the same distribution every time. And so what I learned from this is that training in an order agnostic model is actually really hard, and the reason is because the space of all permutations is huge. It's factorial in the dimension of the data, and therefore a model easily underfits. You can think of inputting and ordering sort of like a dropout, but the space of possible scenarios is huge. And so in this graph, what you see is the fixed ordering trained model in the orange line and the random ordering in the blue line. And the random permutation model underfits severely. And to get good results, I will have to train with a higher capacity model for much longer time. And unfortunately, because of that, the experiment has inconclusive answer to my questions, because we don't have a well-calibrated model, so we can't actually tell whether the sampling techniques is well applicable to convolutional neural networks or not. This leads to future research directions. We can improve the convolutional model architecture. So in this case, I haven't used self-attention mechanism, and obviously it can have higher capacity. Or we can work on sampling algorithms to make this parallel sample algorithm better, in the sense that if we can reduce the space of permutations required to train the model, it will help with training a lot. And we might not need for the model to be well calibrated on all the orderings for us to be able to sample well enough faster. So here what you see is the negative log likelihood compared to some other models. This is my model. This is the model that was in the paper that proposed the parallel sampling technique. And this is the model in the paper that proposed the order agnostic convolutional structure. And for their model, they only trained it on 8 permutations to see significant results. So obviously training on all permutation is a tall order. That is it for my presentation. Thank you very much.